Okay, good afternoon, everyone. My name is Habib Nassar from the University of Glasgow, and as the session chair said, I'll be presenting you our work on multi-material 3D printed bendable smart sensing structures. I'll give you first an outline of my presentation. I'll start by giving you a bit of a brief background on 3D printing and 3D printing sensors and why that can be an interesting way moving forward. Then I'll walk you through our fabrication method of our 3D printer. Then I'll describe a bit about our sensor design and the structure. I'll then present the sensor performance and the results we obtained. In the end, I'll conclude and give you a glimpse into our future work regarding this. So to start, I'll begin by asking why 3D printing, or so more specifically, why 3D printing to produce sensors or sensor structures. Within the manufacturing sector, specifically to do with prototyping, 3D printing is a very powerful tool. It gives us design flexibility, allows for prompt design changes, as well as allows for customization, especially with regards to wearables. Moreover, today 3D printers can print a wide variety of materials, from metals to ionically conductive fluids, biological materials, polymers, etc. But probably one of the most key features is that it can give us an automated fabrication process in which you can send the sensor design to the printer, especially if the printer has the capability of multiple material printing, can give you the complete sensing structure. Our specific goal or specific direction we're going at is 3D printed wearable sensors, more specifically affordable or low-cost wearable sensors to do with rehabilitation, motion tracking, as well as prosthesis. So you can see here some examples of previous work that have been done in the literature of printing ionically conductive materials, conductive paste, as well as conductive polymer composites, all embedded within structures, can be worn either as a glove or a kneecap sensor, etc. So we're kind of trying to go in that direction. But to kind of achieve that in one fully automated process as the fabrication process, we'd like to do multi-material 3D printing. And as of yet, it's quite difficult to do multi-material printing. So we can go into kind of generally two directions. If we look at light-based 3D printing to do with stereolithography, laser sintering, as well as also binder jetting. They can be quite costly equipment and sometimes difficult to customize and set up. So if we want to look at a more readily available option, we can use fused deposition modeling as well as liquid deposition modeling. These can be really powerful because they're open source, usually customizable to your specific needs, as well as low cost. So we get to there. We want to do a liquid deposition modeling. There are multiple ways where we could deposit liquids in our 3D printed structure. If we look at pneumatic systems, they're quite good, they're quite accurate. However, they usually require separate bulky air pressure supply units. And sometimes pressure can be a bit tricky to deal with, as well as adding cost to the whole system. Going with a more conventional direct ink writing method is a way we decided to go. We thought it would be the best way to prove this concept and to make it readily available to integrate with available desktop FDM 3D printers. Now, there's only one thing here to note, that a lot of direct inkwrite liquid deposition systems currently available don't have the ability of retraction, in a sense that you can only deposit the liquid as opposed to retract. And without retraction, you can cause some artifacts because of some oozing in your structure, adding some short-circuiting or things like that which are undesirable. And so we chose an adapted system and a customized system to allow retraction within the fabrication process. Now, if I go through the printer customization that we did, we used the standard desktop RepRap Pro 3D printer. And this has one nozzle to print polymers using this nozzle here with the fan. And we fitted it with our custom system. And our system includes a motor, as well as gears and a syringe to pump the material as well as retract the material as well. This also made a custom fitted housing to fit on the X carriage of the printer next to the FDM extruder nozzle, and we added an extruder needle here. Now, it's important to note that we didn't place the whole system directly on top of the X carriage itself, as many other demonstrations have been done. This adds weight to the carriage, increasing the mass on the carriage, decreases the speed which you can print at, as well as increases some vibrations. So it wouldn't be good for the resolution of the print. So it is clamped on top. However, the housing is fixed on the X carriage itself. Now, okay, looking into this, we need to control the paste flow, and this usually depends on the material used, which I'll talk about in the next slide. But in general, we decided to go for a kind of decreasing in diameter from the syringe to the needle, and not a kind of instant decrease in diameter. So we used a wide Bowden tube connected to a Lure Lock connector, and then to a narrower tube, which then connects to the nozzle and the fitted housing. Now, using the wider tube helps with smoothing the flow of the paste, as well as prevents some blocking. Like I said, the smoother flow with a gradual decrease in diameter. Now, in the extruder needle, a nozzle tip, we use an 18 gauge blunt needle, which is around 0.84 millimeters in diameter. However, this can be changed depending on if we're using a paste with a different viscosity. This tip can be easily changed to either increase the diameter or increase. More to do with paste flow. It also depends on the material itself, or the paste or ink which you are using. And there's some calculations which you can use depending on properties, mainly relating the inertial and surface tension forces to the viscous forces. And if we look at generally the density, surface tension, and viscosity of the paste, we can get a dimensionless parameter, which here is denoted by Z. And by altering those values, if we get a value of Z between 1 and 10, that will give us the best droplet formation. Moreover, to specify the droplet velocity, which we are printing at, which we would code either within the slicer of the 3D printer and the software, or we would code into the firmware of the printer. We'd also follow the equation advice here. Now, in terms of the structure or design, like I mentioned earlier, we're going towards wearables. This is a kind of simple knee brace design which contains a strain sensor. The strain sensor is meant to change in resistance depending on the bending, and the bending gives us kind of an angle of the knee movement to do with rehabilitation. So as you can see, the structure design kind of follows 4 stages of fabrication, let's say, and then with the first one will be kind of the bottom layer, which is the polymer with the channels there. Second, we decided to place some LEDs. Now, the reason I placed some LEDs is we wanted to demonstrate not only that we can print sensors, but we can also kind of expand to print electronic systems using 3D printers. And using these LEDs is to show kind of a proof of concept that we can also integrate passive electronic components within our 3D printed structures to have fully embedded sensor systems. So we place the LEDs in the allotted slots, then print the conductive lines using the conductive paste. You see the middle part here is our strain gauge, as well as the conductive tracks. After that, we print the top layer of polymer on top of these conductive tracks to fully embed the sensor as well as the components. Some considerations to take when printing is the bendability of the structure, because it needs to be wearable, and using specific materials that Chai will talk about in a second ensures good bendability and a lightweight structure that will be easy to strap on. Now, the printing direction of the paste specifically is done along the length of the tracks and not in a kind of infill pattern to prevent some crossover, some cross-linkage. As well, we've made sure that there's sufficient width between the tracks to prevent kind of this any kind of leaking. As well as the layer heights for both the polymer and the paste is done at an integral multiple of what the minimum resolution can be. So this for polymer is 0.1 millimeter in the Z direction, as well as in the Z direction for the paste flow, which is 0.5 millimeters. Now, in terms of the materials used, the polymer used is a glass bend flexi material. There are multiple reasons why we use this specific material. Is that it's bendable enough to give us sufficient performance for our wearable design. Also allows for reversible deformation. But probably one of the key things is that it's mostly transparent. And for our proof of concept, we wanted a transparent 3D printable material to show that we can embed these structures and they can be clearly visible. This is printed at standard 240 degrees Celsius, which is standard for 3D printers. And the nozzle diameter, which it is extruded with, is 0.5 millimeters. The paste, we chose to do a conductive paste. Obviously, you can do a variety of different pastes or inks. We chose a commercially available silver-palladium paste. Now this is really good. It's a really attractive kind of paste because it has excellent adhesion to a lot of materials, specifically to the polymer which we're using. It has also good solderability and high conductivity for application. The viscosity of this paste upon purchase is quite high, so we wanted to decrease the viscosity. We did this by adding a solvent of ethanol. Now, the paste was dried after printing to decrease the resistance as well as to dry it, to cure it. This is done at 100 degrees, 120 degrees Celsius for around 15 minutes. And this showed a remarkable decrease in resistance from around 6 megohms across the strain sensor before the heating to around 1 ohm after heating. And this is consistent with further heating, so it kind of stabilizes there at this temperature. Now, in terms of the performance of the strain sensor, we used this bending setup, this kind of cyclic bending setup, to test the change in resistance with bending. Now, we attribute this change in resistance to the bending of the strain sensor with the individual molecules of the paste coming closer in contact together or farther away upon bending. Now, the original resistance across the resistor under no load was around 0.967 ohms. And the sensor experienced a 6% increase in resistance for a 6% bending strain, which is a good factor of about 1. Moreover, the static measurements show a linear trend between resistance and strain. As you can see from the results here, this is done upon different increments of strain. We didn't stop there. We wanted to use the repeatability of it, especially with a wearable application. So we did a kind of dynamic results as well. So performing this bending cycling for around 250 bending cycles. And you can see that we have stable values throughout these cycles, and this demonstrates kind of feasibility that this method can be suitable and produce a reliable sensor package. And you can see the variation of resistance is also quite clear with the bending, so it's quite encouraging. If you can see, this is the full printed structure with the embedded strain sensor in the middle. So it's fully packaged, and so the whole sensor cannot be damaged, as well as the components cannot be damaged. Also show the LEDs lighting up, so the connectors, the junctions are connected through external wires, they connect to power source. And also show that the different LEDs can be made to light up the different colors depending whether the sensor is in resting position or bent position. So this shows our kind of durable structure, which kind of thing we're going to. Obviously, they need to have it a certain thickness, increases the bendability. These things can be optimizable as well. So these things that can be further developed. In conclusion, we've demonstrated that we can achieve low-cost multi-material 3D printing using FDM and LDM to have this fully automated sensor fabrication method. Ultimately, we produced an embedded strain sensor for a kneecap sensor with embedded passive components as well in conductive tracks. As well as you can see the working strain gauge based on the bending results for this wearable application. In the future, we'd look to expand on this work by achieving more out-of-plane circuitry using a 3D printing mechanism to embed more components and more sensors, probably around capacitive sensing as well. Moreover, we'd like to move towards prosthetics as well. In turn, low-cost prosthetics are usually developed using 3D printers, and adding sensor capabilities is very useful. So this is a step in towards fully automating the 3D printing process of prosthesis with sensors as well. However, you might also question that whether the connections are reliable inside. So far, they are. We have not seen that the paste cracks or that the paste has any issues after drying. However, we'll still look towards looking at some self-healing liquid metal or pastes or inks. That kind of concludes my talk, and thank you very much for your attention.